Hello, I'm LED's magazine editor Maury Wright, coming to you from our HortiCann Light Plus Tech event. Thanks to all you in the audience for joining us today. This is one of our deep dive webcast sessions. It's entitled What's Next? Advances in LED Technology for Next Generation Horticulture Fixtures. Kurt Liepmann, a senior system solution engineer at AMS Osram, will present. I'm sure some of you remember Kurt from prior HortiCanns. He's done some very good presentations in the past on the LED technology. I'm sure he will have a compelling message today. We'll get started in just a minute, but just let me cover some logistics. The presentation is meant to be both live and interactive. Ask a question at any time. Just type it right there into the Ask a Question box. We'll address as many questions as possible once the presentation is complete. If you have any technical difficulties, just type that into that Ask a Question box as well, and one of the members of our technical staff will help you. If you're running a pop-up blogging software, that may be a problem. You should disable that for best viewing experience. And really, if you close down all the other applications, you get the best performance. So I think we're going to have a download of the PDF from the presentation for you and the event resources link. And also, these presentations will be available on demand later this week for all registrants of HortiCann. Now, I'd like to specifically thank AMS Osram for sponsoring this session, and let's get on to the presentation. Welcome, Kurt.
All right, thank you, Maury. So hello, everyone. I want to thank you all for attending today. My name is Kurt Liepmann. I am a senior system solution engineer within the illumination group at AMS Osram. And today I want to share with you some of the latest advances in LED technology for next generation horticulture fixtures. So we'll focus on 3 LED technology advancements today. First, we'll take a deep dive into photon generation efficiency and how LEDs incorporating a horticulture specific phosphor can help improve fixture efficacies and lower costs. Then we'll take a look at an advancement in LED primary lensing designed to optimize how photons reach the canopy, potentially eliminating the need for secondary optics. And lastly, we'll take a look at some of the advancements being made in cost-optimized LED packages that are aimed to improve their lifetime and robustness in harsh horticulture environments. So let's dive into the properties of photons, the different ways they can be generated, the inefficiencies of this generation process, and how LEDs incorporating horticulture-specific phosphors can improve fixture efficacies and lower costs. So in order to fully understand the benefit of a horticulture-specific phosphor, we first need to understand the relationship between light and photons. Light is made up of photons, which are discrete bundles of electromagnetic radiation that display properties of a wave. These photons carry energy that is proportional to their wavelength. This means that long wavelength or low frequency photons like red light carry less energy than short wavelength or high frequency photons like in blue light. So let's look at photon energy in a different way. When we talk about an LED's output, we typically refer to the amount of energy that is being emitted in terms of radiant power or radiant flux. So at equal radiant flux, LEDs that emit longer wavelengths like 660 nanometer red will contain more photons than LEDs that emit shorter wavelengths like 450 nanometer blue. So if we look at the chart to the right, we can see how the number of photons present in 1 radiant watt increases as the wavelength increases. So for example, at 1 watt at 450 nanometers, where would be approximately 3.76 micromoles, where at 1 watt at 660 nanometers contains approximately 5.51 micromoles. And that's an increase of 47%. And this difference in the number of photons per watt is the key point I want you to take away from this slide, as it's the fundamental reason for some of the limitations and efficacy of different horticulture spectrums. So let's take a look at the two ways we can create photons with LEDs. LEDs are either direct emitting or phosphor converted. A direct emitting LED converts electrons into photons of a desired wavelength. This wavelength depends on the material system and the epitaxy layers that are used. Now, a phosphor converted LED is based off of a direct emitting LED, typically a blue around 450 nanometers, and then uses a variety of different materials that have the ability to absorb the high energy blue photons that are emitted from that dye and down convert a part or all of those photons into lower energy, longer wavelength photons such as green, yellow, and red. So when we compare the potential losses in these two options, we see that the biggest differences in their resulting efficiencies can be found when we're looking at their internal quantum efficiency, their external quantum efficiency, and the converter losses. So in the simplest of terms, the internal quantum efficiency, or IQE, represents the relationship of photons produced by the active region within the dye versus the amount of electrons that are injected. Whereas the external quantum efficiency, or EQE, represents the relationship of the photons that are emitted out of the LED dye. So the differences in material systems, epitaxy layers, dye construction, these will all lead to different internal and external quantum efficiencies. Now, the third and biggest efficiency difference between these two methods can be found in the converter loss, as, of course, direct emitting LEDs don't use a converter, so there is no loss there. Now, the result of this is that direct emitting LEDs are generally more efficient than phosphor converted LEDs, except for green. Direct green is terribly inefficient, but as it's not a commonly used LED in horticulture, we're not going to get into that today. So as I just mentioned, phosphor conversion works by absorbing some or all of those high energy blue photons and emitting low energy, longer wavelength photons. Now, this loss in energy is known as Stokes shift, and we'll get into the impact of that here shortly. But more importantly, the conversion is not 100% efficient, and this efficiency of a converter is going to depend on many variables, including the materials, the formulations, and of course the target spectral content. So how many photons do we lose during phosphor conversion? Well, table 1 shows the relative photon flux of some of the commonly used CCTs and CRIs, LEDs that are available, versus a deep blue 450 nanometer LED that these LEDs would be converted from. Now, for this comparison, we're looking at 2 square millimeter size dye that are being driven at 350 milliamps, so approximately 1 watt, and at a junction temperature of 25 C. So in this condition, we would expect a 450 nanometer blue LED to emit approximately 3 micromoles. As we progress to warmer CCTs with higher CRIs, we can see that the relative photon flux decreases as the percentage of red photons generated specifically between 600 nanometers and 700 nanometers increases. So the more red photons we are trying to create through down conversion, the less efficient the converter, and we are left with fewer emitted photons overall. This process actually is so inefficient that a phosphor converted red LED would emit barely more than half of the photons that it started with at the dye level. So if we look at the last 2 columns in this table, we can now see the impact of Stokes shift on the LED's radiant flux. So while photon flux is the important metric for horticulture, but as I mentioned earlier, LEDs are typically measured in radiant flux. So the radiant flux output of each of these LEDs compared to its blue pump is lower than the relative photon flux that is being emitted. So for example, while a phosphor converted red has 53.3% of the photons remaining that the deep blue had, the total energy that's being emitted is only 36.7% of that bare LED. So I just showed you how inefficient it is to generate red photons through down conversion. So how does that compare to a direct emitting 660 nanometer red LED? So same conditions as before. we can see that a phosphor-converted red LED emits less than 40% of the photons of that of a direct-emitting red LED. And if we look specifically at the red photons between 600 nanometers and 700 nanometers, its relative output is even less at only 30%. So the SQD that we see on the bottom left, it shows the normalized photon flux output of both the phosphor-converted and a direct-emitting red LED. So as you can see, the result of phosphor conversion creates a relatively broad red spectrum. The centroid wavelength of this is around 660 nanometers. However, about 20% of the photons are actually extended out past the PAR range and into far red. This would further reduce the LED's photosynthetic photon efficiency value. The SQD on the bottom right is actually scaled to 1 electrical watt. And now you can clearly see in a graphical representation of just how many fewer photons are being generated in a phosphor-converted red LED versus a direct-emitting red. So, you have to ask yourself, which of these two LEDs is going to be a better use of your power? Now, this is a worst-case scenario. I don't know of anyone using phosphor-converted red LEDs in professional horticulture applications. So you might be asking, why am I even bothering to show you this? And the whole point here is I wanted to highlight just how much less efficient it is to generate red photons through down conversion versus through direct emission. Because one of the most widely used LEDs in horticulture fixtures today generates red photons through down conversion. And that, of course, is the white LED. Now, white LEDs have become the majority LED used in horticulture fixtures, and there's several reasons for this. One, availability. White LEDs can be found in a wide variety of CCTs and CRIs, package types, power levels. You asked for it, we have it. The wide availability of white LEDs has led to much lower costs due to the economies of scale. White LEDs will typically offer the best total photon per dollar proposition. The broad spectrum of white LEDs can fill in wavelengths that aren't available in direct colors. And lastly, that broad spectrum also increases human comfort for workers that are tasked with inspection or harvesting of the crop. So traditional white-based spectrums like the one shown here often have a significant amount of phosphor-converted red content. Now, because of this, the spectrum's max efficacy is limited. However, many growers and manufacturers have specific spectral requirements, and they're not willing to change the composition of that spectrum. So what if there was a way that we can replace the converted red photons with a more efficient direct-emitting red photon without altering the original spectrum's photon flux ratio? Well, we can swap out traditional white LEDs with something that's specifically tailored for horticulture, as we call our Horti White. So here you can see on the bottom left a comparison of the spectral content of one of our Horti White options versus a traditional 4,000 Kelvin 80 CRI white. In this case, the Horti White contains approximately 15% less red photons. That lower red content then allows it to be combined with a direct emitting hyper red LED to match the target spectrum's photon ratio. And now, because more of these photons are being emitted from a direct emitting red, the result would be greater efficacy. So we offer our Horti White in two different packages. Both the Oslon Square Horti White and the Osconic S5050 Horti White are ideal white LEDs that enable maximum photon efficacy over existing traditional white and red solutions for horticulture applications. Now, known for its superior robustness, high reliability, long lifetime, and very low thermal resistance, the ceramic-based high-power Oslon Square Horti White with a primary lens is the derivative of our flagship Oslon Square product family, with a comprehensive horticulture portfolio from AMS Osram. In addition to the outstanding efficiency values, greenhouse operators benefit from a radiant flux of over 1 watt and a photon flux of almost 5 micromoles, with an efficacy of 2.5 micromoles per joule at 700 milliamps. Now, the new HortiCann S5050, which, as the name suggests, is a 5 millimeter by 5 millimeter LED, is based on a QFN lead frame and EMC package. Contains an array of dye, and it is a 1 watt device. It offers superior corrosion protection, and the HortiCann brings its robustness stability to another level, further enhancing its suitability for professional horticulture lighting applications. Now, the right LED really comes down to your specific application. In general, if your primary goal is cost and efficacy, we probably want to take a look at the HortiCann S5050. And if your primary goal is lifetime and optical control, then the Oslan Square is probably your best bet. That being said, the HortiCann S5050 still meets and exceeds all industry lifetime requirements. So don't think that it's not, lifetime's not good on that product. Certainly it is. And you can see, obviously, here on this graph, the typical values for both of these LEDs. Now, we offer several different bins that have a variety of varying blue and green ratios. Here you can see the color bin for our Oslan Square. There's 4 bins. The H1 bin is up in the top right. It offers the most green, while the H4 bin in the bottom left offers the most amount of blue content. Our HortiCann S5050 has a slightly different binning scheme, which is only comprised of 3 bins, but the concept's the same, and so is their position in the color space. And again, here, the correct bin for your application is going to depend on what your target spectrum is. So let's take a look at how a Horti white-based solution can compare to a traditional white-based one. So for this study, we targeted board-level performance at approximately 1,800 micromoles at 3 micromoles per joule. We did not take any optical or driver losses into account. We're just looking at the board level. For the spectrum, we analyzed and evaluated several different spectrums that are commonly being used for indoor applications. And we determined that for this, we would target a red-blue ratio of approximately 2.5 to 1 and have a photon flux ratio of 16% blue, 42% green, and 42% red. So for the baseline, we used a combination of 4,000 Kelvin 80 CRI HortiCann S5050s in combination with 660 nanometer hyper red Oslan squares to match that red-blue ratio and that photon flux ratio. So for the analysis, we're going to take a look at how the solutions using the 3 different bins that are offered with the HortiCann S5050 Horti White at that same 2.5 to 1 red to blue ratio, how it's going to impact the photon flux ratio, the direct red contribution, efficacy at equal LED cost, cost at equal efficacy, and lastly, for the human comfort aspect of lighting, we'll evaluate the color appearance and the color rendition. So here you can see the SQD of our baseline solution, which again was 4,000 Kelvin 80 CRI. So let's take a look at how the Horti White compares. So here we see the Horti White M1 bin, and the M1 bin is our greenest of the options. So it has the lowest amount of blue content and the highest green. You can clearly see how the red content that is between 600 nanometers and 640 nanometers has significantly been reduced and been replaced with more efficient direct emitting red LEDs between approximately 650 and 670 nanometers. The blue content was slightly reduced at the 450 nanometer peak, but there is now a little bit of additional blue between 490 and 500 nanometers. The green content between 500 and 560 nanometers has been significantly increased as well. So here we see how the M2 bin, which is just a little bit more blue, solution would look. We now have a higher blue peak and a slightly lower green hump. This enabled us to increase the contribution from direct red. It allowed us to increase it, and we still maintained a red to blue ratio of 2.5 to 1. And finally, we see the M3 bin solution, and just like how the M2 bin looked versus M1, we again have an increase in our blue peak, a decrease in our green, and again, we were able to increase the amount of red coming from direct emitting red. So now that we have all four solutions overlaid on each other, you can see that we have fundamentally changed the shape of the spectrum. However, again, all four of these spectrums still have that same red to blue ratio of 2.5 to 1. Again, the most significant change here is happening in the red range, specifically between 600 and 640 nanometers, where a majority of those phosphor converted inefficient red photons that were emitted from that blue LED, or from that white LED, have been replaced with a direct emitting red LED in between 650 and 670 nanometers. The shifted phosphor of that Horti white is going to increase the green content in the lower portion of the green between 500 and 560. And blue, for the most part, is relatively unaffected, though the peaks are moving around a little bit. Now, any variation you do see here in the data of the actual wavelength of the blue peak is just because of the data that's been used. The target peak wavelength is the same for our Horti white as it is for all of our general white products. So again, all of these solutions maintain that same red to blue photon ratio of 2.5 to 1. And depending on how you evaluate a spectrum, and in this case, we're evaluating the photon flux ratios in blue, green, and red, one could argue that all four of these spectrums are still pretty similar. The M1 and M2 solutions do have less overall red and blue content and more green content compared to the baseline solution, whereas the M3 solution has more red and more blue, but less green content. So in this case, one could argue that the M2 solution is probably the closest match when you look at all three wavelength bins. Now, since Horti white is a single phosphor, you can mix two bins to adjust the blue-green ratio in a linear fashion. So you could theoretically mix M2 and M3 together if you needed to get an even closer match of that baseline. So here we can see how using Horti white allowed us to significantly increase the contribution of direct emitting red photons in the spectrum. The direct emitting red only made up 8% of the baseline spectrum, and this severely limits potential efficacy, whereas the Horti white allowed us to increase that contribution 3 to 5 fold, up to almost 37%. 37% for the M3 solution. So again, the more direct red contribution, the greater the efficacy we can get. Now, for this analysis, we held the LED cost equal to get an idea of how Horti white would impact overall system efficacy. We can see that we saw approximately a 10% increase in LED efficacy with the M3 solution. Again, the M3 solution being the one with the most blue content. We were also able to reduce part count. I lost my slide. We were also able to reduce the part count by up to 24%. Less LEDs mean less space for the required placement as well. So here we see that we decreased our LED area placement requirements by about 36%. See, now where Horti white really shines, however, is when we're evaluating the system cost when compared to the baseline solution at equal efficacy. So let's say you're happy with your system efficacy now, but you just want to reduce costs. Well, we were able to reduce LED costs by up to 62%. This is thanks to the greater contribution of the more efficient direct red that then allowed us to drive both the white LED and the red LED harder without negatively impacting efficacy. So this results in an LED count reduction of up to 71%. Both the M2 and M3 bins had fewer than half the number of LEDs than the baseline. And this reduces the area by up to about 75%. Now, you still have to manage the same amount of heat as the system efficacy hasn't changed, but the significant reduction in area could enable you to potentially optimize your fixture design that could lower the mechanical costs or potentially modify the shape in a way that could reduce shadowing in a greenhouse installation. Now, some of you may have looked at the resulting spectrums that I just showed earlier and thought, boy, those are going to look ugly and are going to look pretty red. Well, as you can see in the graph below, this isn't the case. While yes, there is a large red peak in the Horti white spectrums, this peak is at 660 nanometers, which is at the far edge of our eye's sensitivity. So it contributes very little to the solution's appearance. So here we can see that where the solutions sit on the CIE 1931 color space. Both the M1 and M2 solutions have a slightly greenish appearance, which may or may not be appealing. However, the M3 solution lands solidly in the ANSI 5700 Kelvin quadrangle and has a daylight white-like appearance. And of course, appearance is subjective, but it could be argued that that M3 solution has a better overall appearance than the slightly pinkish hue of the baseline solution. So what about color rendition? While not a horticulture specific metric, it's still somewhat important for crop inspection, right? So the CRI value for the three Horti white solutions is slightly lower than that of the baseline. However, they're all still above 70 CRI. The M2 and M3 are actually quite close to 80 CRI. Things do get a bit more interesting when we look at the R9 value. Now, for those of you who are not familiar with CRI and R9, the R9 value represents the source's ability to render red. And this could be important for crops like tomatoes or roses. All four of these solutions have an R9 value that's greater than 0. And that is the typical minimum value for a traditional 80 CRI white. Yes, R9 can go negative. However, R9 doesn't tell us much about the way the source is rendering red. So if we evaluated these spectrums using TM30, we would find that the low R9 value for the M1 solution is due to the fact that it's actually undersaturating red, whereas the low R9 value for M3 is actually because it's oversaturating red. So under the M3 solutions, red would look very bright, bold, and vibrant. Now, of course, all the gains in efficacy and the cost advantages that I just showed mean nothing if these Horti white solutions have a negative impact on growth, right? So we're currently running a growth study with Michigan State University in their controlled environment lighting laboratory. The objective of this study is to compare the plant growth, the morphology, and leaf coloration under both traditional white plus red spectrum and Horti white plus red spectrums. For this test, we're using two different types of lettuce, a red leaf and a green leaf. A lettuce was chosen due to its short growth cycle. We're using 4,000 Kelvin 80 CRI, and we're going to compare a Horti white M1 and a Horti white M3 spectrums, and these are the same spectrums you just saw me previously evaluate. We went ahead and excluded the M2 solution as we wanted to test the more extreme solutions. And since M2 was fairly similar, it made sense to leave it out. The initial hypothesis is that the spectral variations of the M1 and M3 aren't different enough to see any differences. So if that holds true, we can assume that that would be the same case for M2. The environmental conditions for the test are listed here as well. So at the end of the 30-day grow trial, leaf coloration, shoot fresh mass, shoot dry mass, and plant diameter will all be compared. Unfortunately, we don't have any test results as of yet, as we did just start this trial. In fact, the picture that you see here on the right is an update I got from yesterday. The top rack is the M1 solution. So as I mentioned, it was going to have a green appearance, and you can see that here. The middle rack is the M3 solution, and the bottom rack is the 4,000 Kelvin 80 CRI baseline solution. As of right now, there are no visual differences in the crops. So we'll, of course, share these results when we have them. So if you're interested, please make sure to reach out to me. And just as a side, I did ask the people that are working at this study, of the three solutions, when you're looking at the crops, which one do you prefer to use for inspection? And they all agreed that the middle rack, so the M3 solution, was their preference. So now let's take a look at an advancement in LED primary lens design that can optimize how photons reach the canopy, eliminating the need for secondary optics, thus improving efficacy, lifetime, and potentially reducing the number of fixtures required for high bay installations. So due to the relatively narrow beam distribution of a traditional Lambertian LED, fixtures using this distribution must either be mounted with a tight pitch or at a greater distance to the canopy in order to achieve a full uniform coverage. However, both of these options have drawbacks. If more fixtures are installed at a tight pitch, not only does this increase the system cost, but it could increase the amount of shadowing and thus reducing the amount of natural daylight harvesting in greenhouse installations. Alternatively, mounting the fixtures at a greater distance to the canopy would require each fixture to then emit more photons in order to maintain an equal PPFD, which would require more power. The increased mounting height could also increase the cost of installation and maintenance, not to mention the height of the ceiling is likely fixed, so that's going to limit the maximum mounting distance as well. Now, fixtures using a wider batwing-like distribution can be mounted closer to the plant canopy and have a greater pitch. This reduces both cost and power consumption. So having fewer fixtures can also improve daylight harvesting in greenhouses as well because it'd be less shadowing. Now, there's a couple different ways we can achieve such a distribution. We can use secondary optics to redistribute the photons emitted from a Lambertian LED, or we can use an LED that is optimized for high bay horticulture lighting. And that LED is the Ozone Square Batwing. Based off our industry-leading Ozone Square, this LED will be offered with a unique, innovative batwing radiation pattern, which will evenly illuminate plants for uniform growth without the need of additional optics, all while reducing the number of luminaires. So they'll be available in all the primary horticulture colors, the 450 nanometer deep blue, 660 nanometer hyper red, the previously discussed Horti white, and 730 nanometer far red. All these LEDs are a 2 square millimeter LED die, except for the far red, which is a 1 square millimeter die. And that's because most designs don't require nearly as much far red content as the other colors. So you can see all of our typical values here. So here we can see the comparison of the two methods of creating a batwing distribution that I mentioned earlier. On the top, we can start with a traditional Lambertian LED. We can then place a secondary optic over this LED. Now, adding a secondary optic not only adds cost, but it will add additional optical losses. A secondary optic could lead to anywhere between a 8 to 10% reduction in photon flux. Alternatively, if we use the batwing, Ozone Square batwing, we can eliminate that secondary optic, so not only lowering costs, but also improving optical efficiency at the same time. Flux maintenance is also going to be improved using a bat-winged LED versus a traditional Lambertian LED with optic, because as over time, that constant bombardment of high-energy blue photons will eventually degrade even the highest quality of optical plastics. So lastly, let's take a look at some advancements that are being made in more cost-optimized LED packages aim to improve their lifetime and robustness in harsher horticulture environments. Here we see a cross-section of a traditional lead frame LED package. We have an LED die that is bonded to a lead frame with wire bonds that is then surrounded by a molded housing, and then that cavity is then filled with an encapsulant. So each of these components has an impact on the LED's performance, robustness, and lifetime, which we'll explore deeper. So the first thing many think about when selecting an LED is its housing material. The LED housing provides a physical structure for the LED package for processing and handling. The housing plays a large impact on the flux and lifetime characteristics, as well as a portion of the photons that are being emitted from the LED die itself will come into contact on the inner walls of this package. Now, because of this, reflectivity, thermal stability, and photostability are all key considerations when selecting molding materials. Now, the two most commonly used materials for lower power lead frame LEDs are an epoxy molded compound, or more commonly referred to as EMC, and a thermoplastic called PCT, which has a rather long chemical name, and I'm not going to try to pronounce it today. On the chart to the right, we can see a variety of different molding, how these materials compare. On the x-axis, we have yellowing resistance, which is critical to LED flux maintenance and lifetime of that LED. And on the y-axis, we have reflectivity. The size of the bubbles represent cost. PCT offers a slightly better reflectivity than EMC and at a lower cost. Now, while PCT is less resistant to yellowing, it's a very mature material, and it has improved greatly over time. Today's best PCT materials easily match, if not exceed, the performance of EMC materials of the past. Coatings like titanium dioxide can also be used on the inner walls to increase reflectivity. Now, some LED manufacturers may choose to use lower quality thermoplastics like PPA in order to keep costs down. I don't recommend selecting an LED that uses PPA for horticulture applications or for any professional lighting application, as they exhibit extremely poor photo and thermal stability characteristics. Now, the primary purpose of the LED lead frame is to provide a reliable mechanical connection to the printed circuit board. This connection provides a path for electrical current as well as a path for thermal dissipation. The LED lead frame also contributes to the overall flux output, as those same photons that are being reflected off the inner surface of the LED housing may also come in contact with this lead frame. Now, in order to maximize reflectivity, the lead frame is often plated in silver. Now, silver is a highly reflective material. However, it is quite susceptible to corrosion from a variety of volatile organic compounds, or VOCs, especially sulfur. When sulfur interacts with silver plating, it goes through a process known as sulfuration. This can leave the lead frame brown and brittle, as we see in the image in the upper right here. This browning can lead to a reduction in flux, as the lead frame is now less reflective. This also can lead to a color shift for phosphor-converted LEDs, as there are now fewer photons that are being down-converted due to the lower reflectivity. The corroded lead frame is now also more brittle, and this could potentially lead to increased risk of wire bond failures. Now, in order to minimize the impact of sulfuration, a ceramic coating can be applied to the lead frame, as shown in the image in the bottom right. Thicker coatings provide greater protection, but can also reduce the reflectivity. Now, encapsulants fill the cavity inside the LED housings that surrounds the LED die, and it serves several purposes as well. Its primary function is protection. It protects the die and the wire bonds during handling and processing, as the top of this encapsulant provides the surface for a pick and place to grab from. But it also provides protection from the environment, namely humidity and VOCs. For this reason, it's important that low permeability materials are used. Encapsulants also have an important role in maximizing photon extraction from the LED die as well. There's a large difference in the refractive index between the dye and the atmosphere. The greater the difference in the refractive index, the more likely the photons are reflected back into the dye rather than escaping out into the atmosphere. So the encapsulant helps to serve as an intermediate medium, and they come in a variety of different refractive indexes. Now, LED encapsulants can be made in a variety of different materials, but are typically made of silicone due to its inherent heat and resistance and durability. Modern silicone formulations have come a very long way in improving their refractive indexes and are typically referred to as an HRI or high refractive index silicone. It's important to note that HRI silicones are typically harder than LRI or low refractive index silicones. This does help to improve its permeability, but can increase some of the internal stresses of the package. For phosphor converted LEDs, this encapsulant is also responsible for the suspension of the converter elements. Now, the primary purpose of the wire bond is to electrically connect the LED dye to the lead frame. When it comes to the alloys that are selected, there are several factors that need to be considered, such as corrosion resistance, strength, reflectivity, and cost. And like most things in life, there are trade-offs and compromises that need to be made. While gold offers superior corrosion resistance and tensile strength over silver, it comes at a cost, literally, and exhibits poor reflectivity at wavelengths below 500 nanometers, as you can see in the bottom left. And this, of course, is a big issue, as the typical pump wavelength for white LEDs is 450 nanometers. Now, silver, with its superior reflectivity, can actually increase the LED's flux by as much as 2%, while lowering material costs by up to 70%. However, again, the trade-off is the tensile strength is approximately 15% lower. Now, because of this trade-off in tensile strength, combined with the hardness of the low permeability silicones, as I just mentioned, careful attention needs to be made to prevent wire bond breakage due to thermal cycling. So in this case, alternative wire bond routing or looping can be used to improve the reliability for wire bonds. And you can see on the right side here what you would see as a traditional wire bond routing versus some alternative options to help reduce those issues. Now, the OzConic E2835 family is a comprehensive 2835 platform which offers key features that are typically reserved for your 3030 mid-power LEDs today. And these include the topics that I just discussed, such as the use of high-quality PCT, ceramic lead frame coatings, low permeability encapsulant silicones, and optimized wire bond design. The OzConic E2835 is currently available in a 90 CRI quantum dot, but a 80 CRI is launching later this year, and you can see the typical values shown. Now, when you select LED components for your fixtures, it is crucial that you select LEDs that have gone through industry standard tests for hydrogen sulfide, humidity, and temperature cycling. Here we can see that by incorporating all the advancements that I had just previously mentioned, we have enabled the OzConic E2835 to pass these industry standards tests. Many low-cost lead frame LEDs available in the market were not developed with these conditions in mind and may fail the test. So that is something that can be considered when you are looking at LEDs like this. So again, I want to thank everyone for attending. If you do have any technical questions, or maybe you have an idea for a grow trial that you'd like to think that the Horti White might be a good option and you would like to partner up, please don't hesitate to reach out to me. And if you have any other LED related questions, please feel free to reach out to my colleague, Mark Dybel. And with that, I think we should have some time for some questions.
Yeah, absolutely. Thanks so much, Kurt, for an excellent presentation. And I want to correct one thing. I misspoke earlier when I said that the presentation will be available in Event Resources. And we often do that when we do a standalone webcast. But because this is a series of presentations tied to this entire conference. That's not practical. So all of the presentations will be available on our website, on our HortiCann website, pretty much in the same kind of format you would get the proceedings from other events in. So that will be coming, although not in the next few hours. It will be a few days. So with that said, let's get to some questions. And first up was the attendee said, I do not want to change my fixture's spectral power distribution, can White still be used?
So that's a good question. And that really kind of comes down to how you're going to evaluate what your spectrum looks like. If you're referring to just the exact shape of the spectrum, then it would be a little bit of a challenge to incorporate Horty White. However, if you're looking at the SPD as I've got this much energy in blue, which 400 to 500, I've got this much energy between 500 and 600, and I have this much between 6 and 7, we can incorporate the different bins of the Horty White with additional red LEDs in order to kind of match those together. So having the 3 different bins allows us to match a majority of different types of spectrums that could be made with traditional white LEDs.
And did I understand correctly that the Horty White is really a single phosphor? I mean, it's just one component phosphor?
Yeah, exactly. So the difference is, and you can kind of see that on those graphs that I was showing, is it's just the amount of phosphor that's being added for each of those bins, right? So the more we're adding, the less that blue peak and the greater that green hump is. But it is just a single phosphor line. So that's why you're not seeing like a curve like in a traditional LED where you are combining different amounts of reds and whatnot to that phosphor formulation.
But that formulation does deliver a little bit of red energy, just more energy in the green region, and you get the bulk of the red from the monochromatic LED.
Yep, that's the idea.
So this attendee asks, you show the system efficiency is higher and cost is potentially lower for the M3 bin with the higher blue content. Is there any benefit of using M1 bin with higher green content?
So yeah, I mean, that it would come down to how much green content you want in your spectrum. So if your desire is to have a lot of green, you're not going to get that by using M2 or M3 bins because of the lower content. So that's when an M1 solution might make the most sense. So it really just, the selection of the bin kind of comes down to what your spectral goals are. If your pure goal is just efficacy, M3 is likely going to always be the answer.
This person asked, I had trouble following the low photon flux of the PC LED at 660 nanometer. Nitrides typically have high internal quantum efficiency and high absorption, so I'd expect the photon flux to be at least 85% of the pure blue. Can you clarify how you got the very low value you reported?
So the values I got are based off of the phosphor mixes that we're using. Again, the point that I was trying to drive home wasn't so much that, hey, phosphor conversion red is so super inefficient, which it is a little bit efficient, but even at 85% efficiency, right? The whole point is that a blue LED already starts with less photons than a direct emitting red does. So even if you could convert every single photon out of a one radiometric watt blue LED, you still only have 3 micromoles, whereas that direct emitting red LED is already at 4 micromoles for the same amount of power. So that was the point I was trying to really drive home, was that no matter how efficient a converter is going to be, blue will always have less photons than red. So whenever you can use more direct red, the better you are. That was kind of more what I was trying to get at.
This attendee asks, have you added far red LEDs to Osline Square series, and also you have intensity profile and uniformity data? Oops, my My screen just scrolled without me intending to, and I lost that question. I'm sorry. Here's another one. Horty White can be used in the packaging of 28-35 or 30-30 footprint?
Theoretically, there's no reason why it couldn't. It would really kind of come down to demand, right? So we started with our two products that we felt were going to contribute the most to the industry, as far as our most efficient being our 50/50 and our highest reliability, most robust part being the Aslan Square. But I would imagine if we get enough demand that it makes sense to incorporate that phosphor into a 30/30 or the Osconic E2835, there really is no reason why that can't be done.
And I guess this is a system question for any kind of solid state lighting, but do drivers sitting on top of the lights affect the life of the LEDs with the extra heat from the driver?
I mean, theoretically, if it's contributing enough heat into the system, it could. I imagine that the thermal conductivity between the driver and the heatsink is going to be pretty poor. So it probably doesn't contribute much to the temperature on the heatsink. Therefore, it's probably not increasing the LED's junction temperature. It's probably not even measurable.
Yeah, here's a question that is probably could be discussed forever. But which LED combination do you suggest for microgreens now?
Unfortunately, as I'm not a plant scientist, and I probably couldn't grow anything if my life depended on it, I don't have an answer for that, right? That's kind of why we're working with Michigan State, right? The idea here was we wanted to make sure that, hey, we've got an idea of how we can really improve efficacy in a horticulture spectrum, but we don't really know whether or not that's going to have an impact on its growth. Can we study that? And so that's what we're doing. And hopefully what we'll find out here soon is it either does or doesn't. Hopefully it, at worst case, hopefully has zero impact. At best case, hopefully it actually improves. But stay posted. We'll have some results for you hopefully early October.
And I did find that where that question went in the console. So we'll try it again. Have you added far red LEDs to Aslan Square Series? And also, do you have intensity profile and uniformity data of the LEDs with batwing primary lenses? At the end, when and how could you release analysis data output for Horta White plus Hyper Red LEDs?
All right, so that's a three-part question. Okay.
Yes.
So the first part. So no, we have not made a Aslan Square far red. They can be had in that batwing, which we're calling it the Aslan Square, but it's still a 1 square millimeter part, as well as our Aslan SSL package. Now, the only difference is just the die size. So the Aslan SSL is still footprint compatible with the Aslan Square, so it can be dropped in on the exact same footprint. The reason we don't see any reason to make a 2 square millimeter version of it is just, again, the percentage of far red that's usually present in solutions that we've worked with customers hasn't really justified a reason to create such a high power version of that die. Second part, the graphs. Yes, so we do have all the data as far as its distributions. You can just reach out to myself and we can get in contact. We can get you that data. We do have that present. And I think I forget what the third part of that question was already.
It was how could you release the analysis data output for Horta White plus Hyper Red?
Okay, so we haven't really thought that fully through yet. I mean, imagine once that grow study is done with Michigan State, we'll work with them on, creating some kind of output, presentation or white paper, something like that, with all the different analysis that we're going to do. So we are still very much in the middle of that. We don't know how that's going to work out yet. So we'll have that hopefully shortly.
Okay, well, that's it for presentation for questions. So we'll wrap it up. On behalf of LEDs Magazine and Endeavor Business Media, I'd certainly like to thank Kurt Liepmann for a really excellent presentation and informative Q&A. For our HortiCann event, we'll be moving on through a very busy day. Next up is a multi-speaker session on light and plant response. It will begin at 2 Eastern, and we will be hearing from Charles Kermis of Blossom, Celine Nicole of Signify, and Ian Ashdown of SunTracker Technologies. Thanks again, Kurt, and thanks all of you in the audience for joining us.